Good morning, sir. A lot, sir.
Yeah. Hi. Good morning. Good morning.
Good morning, sir.
Good morning.
So shall we begin from 10
Uh, can you please repeat? Actually, I missed your.
Sir, now can you hear me properly?
Yes. We can start. We can start.
Okay, sir. If you could please present your screen and see if
Yeah.
everything is working fine.
Right. I will do that. So, are you able to see the screen?
Yes, sir. I am able to see this.
Okay. So, how many candidates are there?
So right now we are 22. Joining number.
Yeah,
Let's
because still we have 5 minutes to go, right? So that's why I was
definitely,
thinking. Hmm.
definitely. So the participants are quickly joining. So shall we begin the session or wait for 2, 3 more minutes?
Uh, as you wish. Actually, we can start. There's no problem. But if we can wait for a few 1 or 2 minutes, then also it will be good actually. So that you know, let's give them the time to join. So maybe 2 3 minutes. I
Definitely.
think after that we'll start. Yeah.
Okay. Okay. Thank you so much, sir.
Okay. Thank you. I think we can start now, I guess. Somewhere or the other, the participants are now saturated. I think it will not go beyond that. Oh, it's increasing, but we can start now, I guess. Think.
Definitely, sir, definitely.
Okay.
Hopefully, all of them will join in another 5 minutes, but definitely let's
Yes.
start.
Okay, fine.
Okay.
So,
A very good,
okay.
sir, allow me to introduce you.
Yeah, yeah, please, please. Yeah.
A very good morning to all present here. I welcome you all to the fourth day of our 1 week ATAL FDP on Foundation of Data Science and its Applications, Advanced. Today we have 3 sessions. In the first session, we have Dr. Alat Kumar from DAIICT. He has joined Dhirubhai Ambani Institute of Information and Communication Technology, DAIICT, in July 2019. He has served as a postdoctoral fellow in Concordia University on March 2017 for a 2 year period as a postdoctoral research scholar in the Department of Electrical and Computer Engineering. Dr. Kumar has focused on the development of implementation of new image priors that can provide elegant solutions for the estimation of point spread functions, solving the highly ill-posed inverse problem of image restoration. His research area includes image denoising, low voltage analog, and mixed signal design. He has published and reviewed several papers in international journals and conferences. Sir, I welcome you. So, shall we begin with your
Thank you. Thank you
presentation?
for the thank you for the introduction. So, okay, so I will share already shared my screen. So let me see like are you able to see the screen here?
Yes.
Okay. So one more thing that I want to ask before I'll start the session. And the thing is like, in case if you are not able to hear my voice, so I would request you to inform me in between so that we can adjust to the meeting settings, because somewhere or
Okay.
the other, if the internet is going up and down and voice is not clear, or some screen problem is there, so it will be better if you just ping me up either on mobile or just you know on the chat, not on chat but here itself, like by speaking,
Okay.
so at least there will
Sure,
be no
sir.
disruption, right? And
Sure.
and the second thing is, like before I start this session, there is a basic requirement that I am, assuming from our audiences, and the basic requirements are like they should have a very good knowledge about neural networks and CNN. So, like at least they should know what neural networks are, like how they perform, and what are the what basically is convolutional neural networks. So, some basic idea about machine learning, forward propagation, it has to be there in order to understand this particular topic. So as the topic is suggested that we will be discussing the deep learning architectures related to natural language processing. So in that, what we will be discussing today is recurrent neural networks. That is one of the basic networks that normally people try to work out for natural language processing, followed by LSTM architectures. So this is the title of my talk today, and we will start with the basics, like we will go with the basics as the slide says. And what that basics will be like, we will start with the motivation, like why we actually want recurrent neural networks, as we already have CNN and neural networks with us, and they are performing very well in the area of machine learning and deep learning. So why we want another architecture which is recurrent neural network? What is the benefits that we are getting from here if we already have CNNs and NNNs? Then the second thing is, after we finish off with the motivation part, then we will move on to the architecture details of the recurrent neural network, and we will understand how 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 this architecture looks like, and what are the basic forward propagation and back propagation concepts regarding this recurrent neural network. So once we finish these 3 points out, then we will discuss the disadvantage of recurrent neural network, and why the another network which we call as long short term memory LSTM architecture has started playing its role. So we will understand all this story from the very basics, so that everybody will be on that same page and will be able to understand what's going on in this particular area of natural language processing. So to start with, first of all, just wanted to get a feedback. My voice is audible to all of you, or like just a quick
So
feedback from my
it
end?
is
Yes, okay,
it
okay.
is audible.
Thank you. So let us start with the motivation, like why we want recurrent neural networks. Okay, so the first motivation that we want, for proposing this new architecture, which is the recurrent neural network, is that all these architectures which we have, like for example, CNN or neural networks, what happens is they actually work for fixed grids. They work for fixed grids. By saying that means the inputs and the outputs of these architectures, that is the CNN and the neural networks, are fixed. They are not movable. So that is one of the motivations, that we want some architecture where the input and the output is varying. So depending upon the situation, we want our architecture to be flexible. So that is first motivation. And the second motivation is the long-term dependencies among the data. We will understand each of them in detail now, but these are the two things. First is or the already existing architectures actually work for fixed grids, and the second is this long-term dependency among the data. We will understand this term in more details in the coming slide. So let's focus on the first one first, that is working for fixed grids. So as you know, we already have multi-layer perceptrons, or what we call as neural networks, in already there with us. And what it requires is, it requires an input X and we get some output Y. So depending upon the problem statement, whether it's an image regression or image denoising or image classification task. So basically, uh, this particular this particular vector, which is X over here, is a one-dimensional vector. So as you can see, the architecture of the neural network actually accepts input in the one-dimensional vector. So even if it's an image, you have to flatten it out into a one-dimensional vector before feeding it into the neural network. So this is the first, first type of architecture which we have, which requires one-dimensional vector. So now, as the researchers found out that this one-dimensional vector will actually, is having a problem in case, especially for the images, because the spatial relationship among the neighbors in the image gets lost once you create a one-dimensional vector out of it. So what we actually now do is, like what they have done is, they created a architecture like CNN here. But now what happens is, the image that now what happens is, the input X which is required for this particular architecture is an image. So some way or the other, they have removed that drawback of flattening the image into a one-dimensional vector and then feeding it into the neural network. So now they moved it to CNN, which actually requires image as an input. So the advantages of the neighborhood relationship among the pixels in the image will be retained. And so definitely it was a huge improvement in the area of deep learning, and nowadays we are finding CNN everywhere. So now this is like based on our requirements. Like first it was a one-dimensional vector, and then we thought of images are not good, that we can, if we flatten it out into a one-dimensional vector, it's not a good approach. So they moved to CNN. Now the another important thing is, if X is a sequence, like let us say, for example, we have a lot of food reviews which are available, like like for Zomato or for some other Swiggy, we have people giving reviews for the food that they normally order from the restaurants. So like for example, if X is a sequence which looks like this, like this pizza looks good. So basically, you will find a tons of reviews for food, but they will be represented in this statement form, like this pizza looks good. So the important point is how to actually use this particular sequence of words to be which architecture will be taking this as input, like this one or this one. So the important thing is, we have to find out ways, like how to actually feed this particular type of sequence into these networks, like neural network or a CNN. So what is important is, the sequence is actually important here. Like you have to actually retain the sequence of words also. By saying that means, if I write like this, this looks good, pizza. If I write like this, though you can understand that something or the other for pizza, it is saying that, pizza looks good. But as far as the, meaning of the statement is concerned, it's not a valid, statement because the sequence is disturbed. So somewhere or the other, you have to actually maintain this sequence. That is, you have to maintain, the sequence of the words like this pizza looks good. Then only you can, then only there will be a understanding of, understanding of the statements. So this is one of the important things, that is X is a sequence, and the sequence and the word sequence has to be important. So you cannot flip around with the words and then you can do something or the other. So that thing is not possible. So sequence is very important. So there are multiple ways of solving this problem. The first problem is, to convert these words which are here, like this is a looks good. So there are multiple ways of solving this problem. So the first way is to convert these, individual words into a vector. So what we do is we actually convert these individual words into a one-dimensional vector like this. So for example, if I take bag of words as an example, which is one of the techniques of converting the words into vector. So bag of words basically, or maybe, one hot encoding. So there are number of ways of, doing it. And then we have TF-IDF method. So all these methods that are existing in the literature, what happens is, they somehow or the other convert the words into vector format. So for example, in this particular, lines, if so if we want to represent this as a one dimensional, one hot encoded vector, so what we will be having is, wherever you will find this in the dictionary, you will put 1 over there and you will put 0 in the rest part of the dictionary words. So what we will say is, let us say we have a dictionary of, let us say, 10K words. Let us assume that we have a dictionary of 10K words, and in that dictionary the location of this is somewhere here. So what we will do is, we will put the rest of the values in the dictionary to the value of 0, and we will only keep this as 1 over there, where the location of this word comes in the dictionary. So the dimension of this vector will be actually somewhere or the other, it's 10K cross 1. So it's a dimension of this vector, this. Similarly, what happens is for pizza, so what will happen is, maybe, it will come out somewhere before this. Let us say it comes over here. And what will happen is, we will replace all the other elements in the dictionary to 0, and we will keep 1 for the word pizza, which is coming in the location of the dictionary. And obviously this will also have a vector dimension of 10K cross 1. Similarly for this and for this. So now what happens is, we are able to represent these words in the form of a one-dimensional sequence which is given over here. So now one can say that, if these sequence of words, if we are able to replace it as these one-dimensional vectors, then one can say, okay, we already know that neural network actually takes input as one-dimensional vector. So why not feed these vectors which are over here as an input to these neural network? We can say that, right? Because I already told you that neural network takes one-dimensional vector as the input. So basically, in order to basically see whether neural network is an actual fit for this particular type of problem or not, let us see that. So we will try to solve this problem, that is this pizza looks good type of thing, using neural networks. So the problem statement that we will consider is the sentiment analysis. So what we will do is, we will understand, we will deal with this problem of sentiment analysis, where what we do is, we try to read the tweets that people, write for a particular product, and then we will, classify it into two categories. One is 0, another one is 1. So what we say is, if a tweet for a particular product is good, we will say that, it has a positive sentiment, so its value will be 1. Whereas in case we have, whereas in case if this tweet is not that appealing, and if it looks like, somewhere or the other, this tweet is not good for a particular product. So if somebody is saying this pizza is not looking good, And in that case, we will say the sentiment for that particular product is 0. So we will say y equal to 0. So in this way, what we will do is we will try to design a neural network and see whether we can solve this problem or not using neural networks. So in order to do that, we already know that neural network has multiple hidden layers. So let us draw one such hidden layer here, and then we will have one more hidden layer. Let us say we call this hidden layer as H1, we call this hidden layer as H2, and then we have one output here, which is Y. So this output has to be, in the two classes, whether it's a 0 or a 1, depending upon whether the sentiment is positive or negative. So now what we do is, because we know that, a neural network takes input as a one-dimensional vector. So what we will do is we will, let us say, create these vectors like this. So we have, four words here, right? This pizza looks good. So this is for this is for pizza, and this is for looks, and this is for good. So what we have is each of these vectors are actually 10K cross 1. Each of these vectors are 10K cross 1. So the total length of this vector will be 50K cross 1, because as you can see, we have actually concatenated these words into in this format. So it's a 50K cross 1 vector. So the important thing is, as I was discussing about the sequence of words, you can see the sequence of words is retained. So I have kept, this here, pizza like this, looks like this, and good like this. So basically, the sequence of the words are retained and it's not jumbled up. So one can say that, we have maintained the sequence, we have converted it into one-dimensional vector. So, I think this neural network will perform for the job that we are actually, that we actually want to do, because, there is no need of coming up with some other architecture. So, why, can anyone tell me, like, what is the disadvantage of using this particular, scheme? Like, can anyone tell what will be the disadvantage? Like, if I do like this, will there be any problems? Can anyone tell this? Anyone? So, okay, so okay, I will tell the reason. Just a second. Okay, so the important thing is, if you can see over here, this particular tweet has actually four words. Okay, so it might be the case that somebody else has written a tweet which is of, let us say, 7 words or 10 words. So in that case, there will be a problem, because as we discussed that these both architectures, which is neural network and CNNs, both work for fixed grids. Like, the inputs are fixed. You cannot actually, increase or decrease the inputs. So, in this particular situation, if the second tweet comes up and if that says, the pizza looks amazing and it's very, delicious. So there will be, 4 or 5 or 6 words in that. So what will happen is this input size will keep on increasing or decreasing depending upon the length of the tweet that actually people are putting it in, websites for a particular product. So that is one of the disadvantages, that is input size keeps on changing. So if that is the situation, this neural network is not fit for for doing this sentiment analysis, because input size are changing. So now the important thing is, okay, if the input size are changing, so let's do one more adjustment. And that adjustment is, like, let us say if you have first tweet that has, let us say, 10 words, and if you have second tweet which has, let us say, 5 words, and then if you have third tweet which is having, let us say, 11 words. So let's do one thing. Let's, take all these tweets with different word size and calculate the max out of it. So if you take 10, 5, 11, 6, 9, let us say, for example, so let's calculate the max out of these two, out of the length of these tweets. So the max of these tweets will come out to be, let us say, 11. So let's do one thing. Let's, let's do one thing. Let me copy this. So if the value of the uh, maximum comes out to be 11. So let's do one thing, let's change the architecture a bit. And what we will do now is we will create 11 such boxes. So what we will do, we will create 11 such boxes like this. So it will be 11 such boxes. So the length of this particular vector will be 11 times 10k. So like roughly around 110k is the length of this one-dimensional vector, where this is the 11th box and this is the first box. So what happens is, like for example, the first tweet that we had, this pizza looks good. Then what we will do is we will actually fill in the values of this pizza looks good. So we will fill in the values for 4 boxes, and for rest of the boxes we will put 0. So for all this we will be putting 0. All the boxes which are in the bottom. And like for example, if the tweet 2 is having, let us say 7 words, so we will fill 7 words and we will put the rest of the 4 boxes as 0. So that solves the problem of varying input, because in this particular situation what happens is, you have fixed the input size by taking maximum of all the tweets which you have in the corpus. So you have taken maximum, and then you are saying, okay, you have 11 as the maximum. So what we do is, whatever tweet is less than 11, you just put the values over there, and for the rest of them you keep it 0. So this is basically what you are doing, is zero padding type of thing for the tweets which have, which are less than the 11, size. But in this situation, what will happen is, there is one more problem. And the problem is, in the testing phase, like for example, you have two different, training and testing sizes, training and testing database for these, neural networks and machine learning architectures. So in the testing phase, what will happen is, in case if you find a tweet in testing phase which has more than 11 words, let us say. So let us say if you have 15 words there, then you cannot do that testing with this architecture, because the maximum size of this particular neural network is 11. You cannot use this particular testing tweet which has 15 words here. So again, things changed, and you are in the same problem. And the problem is, you cannot use these neural networks for sequence in this for this sequence of words. And the reason is, despite of solving all the drawbacks one by one, what we observed is that in the testing phase, if the number of words are more, then somewhere or the other, you are actually falling out into the same drawback, which is varying input size. So that is again, the same problem. And this is the first problem that we have if we use neural networks, that is varying input size. This is the first
So,
problem. Yes.
sir, I have a query regarding this. Uh,
Yeah.
will this work on biomedical signals as well? Like, for
Can you can
example,
you please can you please repeat?
so definitely. So my query is, will this technique, the one that you mentioned about zero padding, will this work for biomedical signals? Because sometimes maintaining the sequence is not possible for biomedical signals, or maybe sometimes the interpretation is different. So if we input zero values, or maybe zero voltages or zero frequency, the
Mhm.
interpretation, the actual interpretation will change. So can this
Yes.
be used in biomedical signals, or some other technique should be?
See, the what I will suggest is, like for biomedical signals, because we have, the time information is also important. Like, whatever is there in the back of that signal, and whatever is in the ahead of that signal, like in terms of the time information. So that
Mm.
spatial, that relationship is also important, right? Like before what is happening and after what is happening, or is it like, is it right
Right.
or not?
Yes,
So
it is
that
very important.
Yes, right. So that is, for that reason, actually, somewhere or the other, we have to go for other architectures, which is what we'll be discussing now. That is recurrent neural networks, which actually retains this information, the spatial relationship. Right now, here, if you observe for this particular neural network architecture, because the length of the sequences are, that is the major drawback here. If you observe, because your ECG signals may have different lengths, right? So in the testing phase, it might be the case that your ECG signal may be of varying length. So that's what I was telling here, that this is not a suitable architecture for working with ECGs, because somewhere or the other, the relationship between these, between the time series data, because somewhere or the other ECG is also a time series data. So the relationship among the samples is somewhere lost if we try to, try to use neural networks here. You understand? So we will try to use recurrent neural networks, and there you will understand, like these recurrent neural networks will try to actually, take the relationship of this sample which is over here, and it will, somewhere or the other, this relationship will keep on going, and the information will be, percolated through this time series data, so that you can make a better judgment in the next sample or whatever processing you want to do. Okay.
Okay, thank you so much, sir. So please continue.
So this is the zero padding thing, which is not efficient. So what I was telling is, this particular architecture, the neural network architecture which we are using, varying input size is still a problem, because in testing phase we have different length sequence. And the second important thing, that is another important thing which is more important, is the weights, which are actually blowing. I'll tell you what that means. So if you see the interconnection of the weights, let us say you have here, 5 neurons in the hidden layer, and then you have 3 neurons in the another hidden layer. So what you do now is, you can recall from the theory of neural networks, you will have interconnection of these weights. So you can see the interconnection of these weights. So the size of these weights will be how much? It will be 110K times 5. So you can see the enormous amount of weights that you have to train during the back propagation, for this single layer only. So with with simple 10 words, with simple 11 words, your weights are jumping to 550K. So it's a very small, tweet that we are actually looking for. We have large, we have sometimes, big lines, big statements or big tweets, and so they are more than 11 words. So you can see how quickly this particular interconnection of the weight matrix jumps. It jumps to 550K immediately. So 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 this is actually one of the major drawbacks, that is, the weights that you will be training for this particular architecture are too high, and it will slow down the process of training, and it will be very difficult for you to do sentiment analysis using this type of neural networks, especially for time series data like this, that one which we are discussing. So it's a time series, it's valid for time series also, it's valid for the sentiments also, where you are actually having words as the input. So definitely these are the two drawbacks that we have, that is varying input size, and then you have weight blowing. So your weights are getting too much to be trained, so it slows down the process. So these two objectives must be kept in mind, this one and this one, and let us see how our new architecture, which is recurrent neural network, will actually solve this problem. So that is our next objective, and we will see that, our architecture RNN will solve both these problems of varying input size as well as the uh, growing of the weights. So so let me show you that. So let us discuss let us discuss again this problem of sentiment analysis. Sentiment analysis. Let me change the color. Let us discuss this again. So in this sentiment analysis, what we will do is, we will do again that same problem which we were doing. That is, if we have a first tweet, and that tweet is, let us say, x1, and we have second tweet, and that tweet is, let us say, x2. So in this particular tweet, we have, 5 words, let us say. So we have x11, x12, x13, x14, x15. And in the second tweet, we have, 3 words, let us say, x22, x23. So let us see how we can use these variable inputs into the architecture, and simultaneously the weight problem also has to be addressed. So what we do is, in this particular example, we will uh, we will create an architecture like this. So we will have one neural network which has a single layer. So these are the This is only first layer, only single layer neural network, which has, some, let us say, these are 5 nodes, so it can be anything, let us say if you have, k nodes here. So we have k nodes. By k nodes means you have k neurons in this hidden layer. So this is the hidden layer which you have. So what we do is we will take these individual words now, because in the earlier case also we were treating this to it as a combination of words, right? The first word, second word, third word, fourth word, and fifth word. So we will be actually using individual words for our, for this particular architecture. So let us take the first word, which is x11, and you know that this first word will actually be a one-dimensional vector, which we have already converted using one-hot encoding. So this one-dimensional vector will be of size d cross 1, where d is the dimension of the dictionary. This we have already discussed, that we will have d columns and d will be the dimension of the dictionary. So now what we do is we actually connect this input, which is over here, to the hidden layer, and the interconnection between them will be denoted by, let us say, w. So this w, can anyone tell me what will be the dimension of this w? Like if we connect this particular input, which is x11, to the k nodes as the hidden layer, can anyone tell what will be the dimension of this particular weight matrix? Okay, so the dimension of this weight matrix will be actually k cross d, because there is an interconnection between the inputs which are here. So you have d inputs and you have k nodes. So the dimension of the weight matrix will be k cross d. So now what we do is, at time t equal to 1, we are actually feeding this word into this single hidden layer. And what we get at the output from this is basically what we are saying as O1. This is the output of the first word. That's why we are calling it as O1. And what is this actually? It's basically a nonlinear function, nonlinearity, that is either a sigmoid or a 10-H nonlinearity, which is operated on the weight matrix W times x11. So this is basically the output of the first layer of the hidden layer, which is f, which and times w x11. This is at time t equal to 1, you will perform this experimental task. Now at time t equal to 2, please note that we are actually moving in time. We are not moving in space dimension. It's a timing dimension. So at time t equal to 1, we have this architecture, and time t equal to 2, what we will do? We will again use this same hidden layer. We will again use this same hidden layer. So this hidden layer, which is here, is this one is same. So this is also, this is, and these both are same actually, and they are not two. They are only single one. Please note, this is the time axis. So these two are not different. They are the same architecture, same single hidden layer. So what will happen now? We will now input a value x12. This is the second word, and the dimension of this is again uh, d cross 1. And let me move it down. So again, once you feed this into this, the weight matrix that it is over here is k cross d. And note that this weight matrix and this weight matrix are same. So they are not two different weight matrices. This is only a single weight matrix, which is this one and this one. Both are same. So this is at time t is equal to 2, you are feeding the second word. And now what we do is, what we do is, like, you will put this particular output of the first word as an input here into this particular hidden layer, and you take the output here as O2. And what will be the output O2 now? Output O2 will be F, and then you have W X 1 2 plus O1. Why O1? Because, sorry, not O1. It will be basically what? It will be, you know, you are actually, you know, multiplying this O1 with another matrix which is W hat, and this dimension of this W hat will be how much? So this is basically K cross 1. So, and this is again you have K nodes. So what will be the dimension of this W hat? The dimension of W hat will be K cross K, because you are connecting K nodes to the another K nodes. So the interconnected weights will be K cross K. So this is the dimension of W hat. So now the O2 that you are getting at an output here will be W dash O2. So now you can see that you have two, you have done it for 2 times, like t is equal to 1, t is equal to 2. Now you can continue to repeat this till you get to the word t is equal to 5. So at t is equal to 5, what will happen? At t is equal to 5, you keep on repeating this. You keep on repeating this. Let me draw it down. So at t equal to 5, what will happen? At t equal to 5, you again you again have this, single hidden one. Then you have the same W, and the size you already know, it's K cross D. This is your XI, this is your X1, 5, this is the fifth word. And the output which is coming from the previous stage will be O4. And this weight matrix W hat, will be all again that same weight matrix, which is K cross K. And then you have an output which is O5 with here. So this O5 will now, what will happen is, it will be actually passed through a sigmoid layer to get the output Y hat. So this Y hat is the sentiment analysis, like whether you want 0 or 1. So this O5 is again, if you can check, this O5 will be again, it's a vector of K cross 1. So this is a vector of K cross 1. So what will happen is, you have to convert this vector into one output. So you have to again, will have again a one more weight matrix W double dash, which is of dimension how much? It will be of dimension K cross 1. So basically, somewhere or the other, you are actually converting your weight matrix using this W double dash. You are converting this vector, which is of K cross 1, into 1 cross 1 vector. Or rather, it will be, not K cross 1, it will be 1 cross K. So because when you multiply the two, it will get 1 cross 1. So basically, the important thing that I want to discuss here is that we had two targets in our mind, that is variable inputs. So the first input was of 5 words. So you can see that at time t equal to 1, you applied first word, and time t equal to 2, you applied second word, and then you kept on doing it. At time t equal to 5, you have fifth word. So now you have 5 such repetitions of this single hidden layer. So please note that this architecture is not of 5 layers. It is only single layer, which is at time t equal to 1, time t equal to 2, time t equal to 3, time t equal to 4, and time t equal to 5. You are actually reusing this single layer always, this single layer only. You are not having these 5 layers. It's a single layer only. So, if you have now 3 words, let us say, so you will repeat this 3 times. And if you have 7 words, you will repeat this 7 times. If you have 10 words, you will repeat it at 10 times. So this solves the problem of variable input size, because each time each time the tweets have different length, you keep on repeating this only. So there is no variable size problem now, because you have only one hidden layer, and you keep on, with time, you keep on feeding the words in the tweet. So this problem of variable input size is gone. And the second problem which we had was weight explosion. That is, we had large number of weights which are coming up, is also gone, because somewhere or the other, you are actually reusing the weights every time. So this weights which you have here, you are reusing it. So these weights, all these weights are same. Even the W hats here, and the on W hats and Ws are all same. They are not different. So you keep on reusing the weights. So for example, if you have used this first tweet for training purpose, then whatever weights you have, this weight and this weights you have adjusted during the back propagation, then when you have second tweet after that, again you will use these weights, same weights for back propagation. So the weights will always remain the same, and it will be of small, though it will be a big value here, but it will not be too much because you are actually using the same weights continuously for multiple number of tweets. So this means the weight problem, which was a big problem earlier, is also somewhere or the other solved because 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 you're because it is basically taking only single word and it's not taking a complete vector, which was in the case when we were discussing neural networks. So this basically architecture which I have shown you here is also represented in the compact form like this. So it's also represented in a compact form like this. If you see the various architectures that in the papers, you will see something like this. So somewhere or the other, what it is trying to show you is that the output of this hidden layer is again fed back to the input of this hidden layer itself. So this is what it's trying to show here. This is basically a cycle which shows the output is fed back into the input. So this is so so the important thing is you have only single hidden. I'm repeating it again. You have only single hidden layer. So there is no multiple layers like this. That is important. So here you can see the output, which is coming up from this hidden layer, is again fed back to the same hidden layer like this. You can see O1 comes out, fed back into this O2, and then you have O2 comes out, fed back into O3, fed back into that same layer. So somewhere or the other, this is expanded in time domain. But if you want to show it in a compressed format, it's like this. So if you have any questions here, you can ask me.
Sir, I have a query.
Yeah, please.
So when we are coding, specifically in Python, then when we are initializing the layers, we generally set a seed so that we can get a same matrix, or we could input that matrix in the next layer. Generally, that seeds is at default or maybe at random. If we set it at a very same constant rate, then the same matrix is generated. Is that what
Yeah.
you're referring to? We are trying to recall the same weights, like when we
No,
are
no,
coding.
this is not, no, this is not related to seed actually. This is related to the weights that we are actually, I'll tell you this. See, you have this hidden layer, right? So in this hidden layer, if I am using this weight, which actually connects the word, so what happens is this is the first word that you fed. And then you actually, when you do the back propagation, what will happen is these weights will be adjusted during the first review that you have taken, like where the number of words are 5. So you have done a back propagation and you adjusted that weights. Okay, you kept this weights like that. And again, what happens is once you go for the second weight, the weights will be the same. It will not be a different weights like W1, W2, W3. So that's what I was telling, that multiple, though we are showing it in a though we are showing RNN in this fashion, as you can see in the papers. And if you see, you have W1 here, W also here, W also here, W also here. So the important thing is these weights W1, W2, W3, W4, they are not different. They are actually same weight, and we are reusing that weight again and again. It's not about seeds. Okay.
Okay. Thank you. Thank you, sir.
And to start with this thing, if you observe here this architecture, for every for every for every layer, you have some output which is going back into the input, and then you have output going back into the input, and output going back into the input of the another layers. So to start with here, there is no input from the left side. So what we do is we actually feed this layer with zero input to start the iterations. So So to complete the discussion, like, output going back to the input, like concept, to start this, we actually feed a zero vector to start the process. So this has to be kept in mind.
Thank you. Thank
Okay.
you so much.
Yeah. Thank you. Yeah. So the thing is, once this is done, so we our two problems are solved. One is long-term dependency and weight problem. No, sorry, varying input size and weight problem. So now the third problem that we were discussing was long-term dependency. So long-term dependency is something like, if you have a large sequence of words like this, if you have, a tweet which is very large, I am not writing the exact statements, but let us say you have a tweet which is this big large, this large having so many words. So if you have some name over here, like, a city name like New Delhi, okay, and suppose somewhere in the end, what we have is, we have, Hindi. So what happens is, uh, the machine should, actually correlate these two words. There should be, they should be able to, correlate that, if somebody is speaking Hindi and if it's New Delhi, then they are somewhere or the other correlated, and there is some connection between them. So the dependency has to be there. So what happens is we want to actually do similar type of correlation. I will give you the example in more detail in the next, slide. But somewhere or the other, we are trying to actually create a dependency between the words. We want to actually see what is the focus actually. So for example, in this particular example which I am showing you here, so for example, if I ask, these are the screenshots of my mobile when I asked, Google, following questions. So what I asked was like, when was WHO formed? So when I asked this question, uh, Google returned back with the answer that WHO was founded on 7th April 1948. Okay. So once this is done, I again asked, why was it formed? Then it gave me this answer. Because of some reason that he's having stored in the database, the answer is given like this. Now, when I asked where are its headquarters, then it gave me the result like, it's in Geneva, Switzerland. So the surprising part that you will observe here is I asked about WHO, which is the main keyword here, first time only. But in the second question, when I was asking this, I have never asked that, there is no WHO involved here. So how it is possible that when I asked this question, it has correlated it with WHO? Similarly, here also, where are its headquarters? Again, I have never asked about WHO, but it immediately realized that we are asking about WHO. So all these questions, the answers to all these questions are basically with respect to WHO only. So that is quite surprising because, this is what I was telling you that, the machine that we are trying to propose, this long-term dependency has to be there. So even though we are asking some questions, it has to correlate it with the main subject line. So this is our main objective also when we are doing, natural language processing. That is, our architecture should be long-term dependent. So this is what the example that I was trying to show. Another one is like, for example, if you have these three numbers 10, 11, and 12, and another one is 4, 8, and 12. So you can see at the end you have 12, like, you have 12 here and 12 here also. But how come, you can, so you have to decide like what will be the answer here for both the things. So machine will be able to predict it if you are doing it through recurrent neural networks, because it actually captures the sequential information which is present in the data. So you can see there, it tries to actually capture the interrelationship between the data. So it will come out to be the value of 13 here, and for it will come out to be 16. Though the last word is 12, but still, because the RNN captures the spatial relationship among the samples, it will give you different results here. And this is not actually possible with other architectures like neural network and CNNs. So as I told you, a simple neural network actually looks like this, where you have, inputs and the outputs followed by in between hidden layers. Whereas in case of RNNs, what we have is we have actually some sort of feedback connection going out, coming out from the hidden layer and going back to its hidden layer. So if you recall, if you are a digital, if you are an electrical engineer, if you see we have these digital gates. I think you must be knowing it. So for example, if you have A, B, and you're getting an output Y, so it's a normal combinational circuit. But if you have a digital circuit which looks like this, where you have inputs A, B, and the output is fed back into the input, then what happens is it's a sequential circuit and memory is created. So similarly, here we are trying to create a memory by actually feeding back the output into the input, and this memory element is actually helping us to carry out this learning process where we have this long-term dependency learning. So this WHO gets propagated into this because of the memory effect that we are trying to create in the hidden layers. So you can see here we have these recurrent, you know, connections. So they are actually creating the memory effect for CNNs, for RNNs. So basically RNN architecture, as I discussed, looks like this, where you have, on the left side you have this neural network. This is your simple one neural network having, this type of architecture. Whereas in case of RNN, I told you, your inputs and outputs will be, continuously recurring back into the hidden layer. So this can be easily expanded in time domain. So this, please note, it's a time domain representation. So this axis is actually time domain. It's not that you have three hidden layers. It's only single architecture, but in time it is actually represented in this fashion. So this is a compact representation. This is the rolled out version of the same expression which is over here. So there are different types of recurrent neural networks that you have in the literature. So the first one, we can say it's a one-to-one neural network where you have single input and single output. So this is similar to the normal neural network that we have. So this particular RNN actually is same as a neural network, simple neural network. So a typical application of this particular one-to-one will be cats versus dog classification, which you can actually do with this particular type of task. The second neural network is one-to-many. So you can see here you have a one input and you will get multiple outputs. So this is the second architecture of RNN, and a typical application of this is image captioning, which is shown on the right side. So what happens is you have single input here, right? So this single input is actually nothing but an image, and what happens is this not this sorry. So what happens is this particular input is actually uh, this side. So what will happen is this basically just a minute. This image will be actually passed into the CNN, followed by convolutional blocks, followed by fully connected layers, and then what we will get is you will get a hidden representation in a one-dimensional vector format. This one-dimensional vector format is this, and then what will happen is you feed this into this particular RNN architecture which is shown over here, and then you can use it for image captioning. By image captioning means what will happen is you will feed an input which is in the form of image, and what you will get as an output will be a caption related to that image. So it will be a man playing guitar. So this actually somewhere or the other is helping out to caption the image, and this is a typical application of that, where you have single input in the form of the compressed representation over here of this image, and then output is multiple, like you have a man playing guitar. So you have four words, and these four words are actually one to many architecture words which is here. So this is a typical application of one to many, which is image captioning. Then you have many to one architecture also, where you have multiple inputs and single output. A typical application of this is this prediction task which is given over here. So you have a time series data, and what you do is you actually feed in these inputs into this, and once you feed this input into this, you will get the prediction of the next state of this ECG signal, which is actually a single point which can be predicted over here in this particular point. So it's a you can do a prediction of ECG time stock time series data using many to one architecture. And then you have many to many architecture also, which is given over here. So you have this input and this input, this as an output, and again you have this as an input and this as an output. So you have two different versions of it. Many to many actually is used for automatic language translation purposes. So this is basically many to many, where you have you are translating from, let us say, English to French or somewhere or the other. Both the languages are different, so if you speak in English, it will not mean the same in, it will not have same words in the another language. So you have different length of languages. So basically that corresponds to many architecture. So here you can see, if I am speaking something in German, doesn't mean that it will be, though it is showing you it's with the same words, but it might be the case that the number of words required to say this statement in German will be different in another language. So for this particular case, though the number of words are same for both the languages, but note that even the orientation may be different. So whatever you are saying here doesn't mean that your another language will use that same word in the starting. So it might be the case that this word which is here in German may corresponds to the last word in the English. So that orientation is different, can be different. So it doesn't mean that whichever word you are using here, the same word will be there in the English. So basically this many to many architecture can be used for automatic language translation purpose also. So these are the typical applications. So now what we will discuss is, let's take 5 minutes break, and then what I will do is I will discuss the architecture detail of RNN followed by LST. So is it okay
Sure,
to take 5 minutes break?
sure.
Okay,
Completely, sir.
thank you. So
Thank you, sir.
we'll start at 11:06. Okay.
Sure, sure, sir.
Okay, so let me start with the architecture of the recurrent neural network. So before going there, am I audible to everyone?
Yes, sir, you are audible and we can
Okay,
see your slide as well.
okay, fine. So now let us discuss the architecture of the RNN, which we have already discussed. So let me just quickly glance through it, like whatever the equations are involved and what they are. So, for example, here, this is particularly the recurrent neural network which we have already seen, and we are, right now I'm showing here that this particular U matrix is actually a shared matrix, which is a single weight only, and it's not multiple W's or multiple U's. And similarly, these W's are all same, and you are going up to time t, which is a capital T. This capital T is actually number of words that you are using in the time sequence, or in the sentiment analysis, or in time series it will be the pixel or the intensity value uh, of the time series data. So whatever, so it depends upon that. So the thing is, this particular X1 can be encoded into n cross n features, and here you have k outputs, let us say. So based on this architecture, we have these equations which are written over here. So we have this hidden layer ht, which is tan hyperbolic u xt plus w ht minus 1. So here you can see uh, at any time instant t, the hidden layer output ht, which is over here, this hidden layer output depends upon the input and the second input which is coming from here. So there are two inputs actually, which actually decides this output, which is given by this, and it's recurring with time. So this is one equation. And finally, at the output, when what you get at the output is yt, which is actually softmax version of vht. So please note that these terminologies though are different from the ones which we had discussed earlier, but all these are weight matrices also. So this is basically w, and this is basically w dash, and this is basically w double dash of our earlier discussion which we were doing. So this is just showing you the pictorial representation that how u's and w's looks like and v's look like. That is interconnections, because sometimes these x1 looks, sometimes it looks confusing, like how this x1 is connected to h1. So what we normally do is we actually take this vector, which is a one-dimensional vector, which transpose it like this, and then we have these interconnections. So this is what is showing you pictorially, like how uv looks like. And similarly, the w, which actually connects the two hidden layers, also looks like this. So it's just showing you that. And these are the dimensions which I have already discussed with you earlier. So these weights, u's and v's dimensions are written in this format, which you can cross check later, but somewhere or the other they are the same dimensions which we have discussed in our starting slides. So the thing is, we have this forward propagation, which basically means you are forward propagating in the direction of the output. And the equations that actually govern this forward propagation are these two equations, which is st, and the final one which you are getting as yt. And the loss that you actually use to calculate these, whatever loss you are incurring during the training process, you are using the binary cross entropy loss or the cross entropy loss, which is given over here, and then you sum it for all the time instants where you are actually getting these losses, and this is actually represented by L. So these are the forward propagation equations. And finally, in the back propagation, actually, normally what happens is, in the earlier architectures which you were doing, which you were using actually, the back propagation was normal, and here the back propagation is through time, because at each instant of time you have to back propagate back. Because if you remember that for time t equal to 1, you were using this as the input. For time t equal to 2, you are again using this hidden layer, but now t2 is as the input. So when you do a back propagation, it has to again back propagate in time. So that is important. So there are actually two back propagations which are happening here, to be practically speaking. The first back propagation that is happening is between these layers. So you have a forward propagation going like this, and then you have a back propagation which is going like this in the vertical direction. And the second type of forward propagation and back propagation which is happening is like this. This is a forward propagation which is happening. This is the second path, and the back propagation is happening like this. So this is the second back propagation. So there are two types of back propagation which are happening, and these weights u actually gets updated and added during both the processes. Like, this u will be updated because of this back propagation also, and it will be then updated again due to this back propagation also. So this has to be kept in mind. So this u gets updates on the back propagation from both the sides, this one as well as from there. And typically, that in back propagation, what you normally do is you actually use weights and UVs and use to update using gradient descent. So the important part is how to calculate these gradients which are given over here. So if you actually are interested in understanding these gradient descent weights, like how we are getting these weights, you can actually, just a second, I'll tell you. I don't want to go into the details here because somewhere or the other time of that is not possible. But what I can do is I can at least show you a bit of this thing here. So you can see here, we have I have this complete list of videos for my lectures which I normally do in DICT. So maybe if you want, you can watch it here. So this list will have all the details of what we are doing. So here you have all the lectures for LSTM, and whatever I am discussing here will be here itself with the details. Like, you can have all the details of RNN, all the derivations that are involved here. So you can watch that in case if you are interested. But right now I am quickly glancing here because of the time constraint.
Thank you so much, sir,
Am I
for sharing
audible
that.
and my screen is visible?
Yes, yes, definitely, sir.
Yeah, thank you,
And
thank you. So am
thank
I
you.
audible? And okay, okay. So now, so I'm not going into this detail of calculating. So if you are interested, you can watch these lectures which I just pointed out to you. So now, the important thing that I want to discuss is what are the drawbacks of this RNN. So the drawback of this RNN is that is the weights that we have here. Let me draw this again just to clearly explain what's going on. So if you have these multiple hidden layers and you have some output here, right? Y hat, which is a sentiment analysis. So you have here xi1, xi2, xi3. So basically, I is the ith tweet, and 1, 2, 3 are the words corresponding to that. So now you can see here, the important part that I want to discuss is that this y hat, which is over here, let me this y hat which is over here, it actually directly depends upon this word. If you see, this y hat directly depends upon this word. And how it is directly dependent, you can see from the equations, it's actually y hat times, if it is w, so wxi5 plus, then you have w dash, and then this is, let us say, O4, so w dash O4. So you can see how this xi5 is directly dependent upon y hat. But now, if you see, this y hat over here is indirectly dependent upon the first word, which is here, xi1. So that is indirectly, in the sense that if you see here, y hat is equal to f wxi5 plus w hat o4. So o4 is what? O4, again, you can replace it by uh, let me draw it, f times then wxi4 plus o3, and then you again replace o3 by, you can recursively write it, and once you do it, there will be a point where you will have xi1. But the problem is, this xi1 is very weakly related to this y hat through multiple multiplications of these non-linearities, which are f times f times f times f times this, something like this. So the important part is, if you take the derivatives of of the loss with respect to xi1, if you take sorry, not xi1, of this weight which is at the first time instant t1. So if I take the derivative of the loss with respect to weight for this particular instant, you will see there will be a multiplication of so many derivatives inside it, and the derivatives are actually somewhere or the other the derivatives of these f function which are cascaded and multiplied with xi1. And what happens is these, if you take sigmoid, as the function, then you will see that its derivatives will it will be less than 1. So if you take the derivative of the sigmoid, it's less than 1. It's like, I think, 1 by 4. So what happens is, you are keep on multiplying a fraction which is less than 1 continuously. And what will happen is, at this instant, the derivative of the loss with respect to w will be 0 in the time instant, time t equal to 1. So if the derivative of the loss with respect to w will be 0, then the updates that you will do at time t equal to 1 will be like this, and this is 0. So it is not updating at all. So what happens is, the dependency of the output y hat on this is very weakly dependent, and there is a problem of vanishing gradients. So it's a vanishing gradient problem, because your gradients are becoming 0 due to this long sequence, which is over here in case of RNNs. So that is one of the major drawback that we have in case of recurrent neural networks. And the drawback is that this particular y hat, first of all, it loses its importance. Like, the long term dependency is gone because of the multiplication of these f's which are over here. These f's actually make this contribution of xi small compared to this xi5. So the long term dependency problem is there, and second is vanishing gradients problem is there, because you cannot the value of the gradients are becoming 0 with respect to this w at time t equal to 1. So that is the major drawback that we have in case of recurrent neural networks. So in order to avoid that problem, what we come up with is the another architecture, which is very famous architecture in the area of natural language processing, and that architecture is called as LSTM, which we are calling as long short term memory. So what happens is, this particular architecture is capable of um, you know having a long term memory as well as short term memory. So it can restore both of them. So it has a capability of handling both the long term relationships also and short term relationships also. So let us see how this architecture looks like. So a LSTM architecture looks like this. So you have you know a block. In this block, what happens is, you have input like this already, which we have already discussed. We have input xit, as we already had it in case of RNN also. And then what we do is, we have y hat t minus 1. That is the output which is coming from the previous block. We have that. And what we do is, we actually join these, we concatenate these two. By concatenation means, if you have xit, which is a vector, and if you have y hat t as a vector, so you actually concatenate these two vectors in a horizontal direction. So you concatenate these two vectors, and then what you do, you pass it through a sigmoidal unit, and this sigmoidal unit is basically a neural network with the sigmoid as the output, and sigmoid applied at the output. Then you do what? You multiply it with the signal which is coming from here, and this signal is basically nothing but the OT minus 1. So this OT minus 1 is the basically what you can say, it's a carry, which is a cell state basically. So it's coming from the previous output. So now what happens is, this particular thing is carried forward and it's added to another block, which is like this. Let me draw it first. So here you have sigma, and then you have this, then you have tan hyperbolic. So both these, all these three are actually neural networks with sigmoid nonlinearity, and here you have tan hyperbolic nonlinearity. And these all these operations are point operations. So by saying point operation means, if you have 1 comma 2 comma 3 vector, and if you have another vector which is 0.2 comma 0.3 comma 0.5, and if you want to add them, then you will do it by like this: 1.2, 2.3, 3.5. So it's a point-wise application. So it's a pointwise addition. So this particular, um, this particular operation, this particular operation, and this particular operation are pointwise operations, and this and this are basically the neural network with sigmoid and 10 hyperbolic nonlinearities. And then what we have is we have another block which has sigma here, and then it's multiplied by again pointwise multiplication, and at the output you have here y hat at the instant t, and then you have a copy of this. You have a copy of this. You take, so this is basically copying. You're copying this, and you are getting another output here y hat t. So both of them are same, but you are just copying it. And then what you have here is you have another output which is coming from here. So this is basically the OT. So this is basically cell state at time instant t, and output of this is again fed back into 10 hyperbolic unit, and then it's fed into the multiplication cell. So again, note that this particular thing is pointwise. So because the one which I am showing you in circular is pointwise, that means if you have a vector, then what you do, you apply a tan hyperbolic on this vector. So individual elements of that vector will be tan hyperbolic, individual elements of that vector. So it's again a pointwise thing. So now this particular block is called as, let me draw it. So this particular block is called as, it's a forget gate, and this particular block which I am highlighting over here is called as input gate. And let me draw it with different color here. So this is basically a input gate, and this particular block is called as output gate. So this is your output gate. So you have three gates. So let us see how LSTM architecture is helping us in maintaining this long-term dependency which is given over here. So we are saying right here that y hat is actually somewhere or the other poorly related with xi1 because you have multiple cascades of these nonlinear functions operated on xi1. So somewhere or the other we want to see how this y hat t can actually correlate with this first line, first word actually on in this statement. So in order to see that, we will focus on the top part of this LSTM architecture. So if you focus on that, what you have is you have OT minus 1, then you have something over here multiplied, then you have addition followed by carrying this OT forward, and then I told you that you have an input here. So this input is coming because of forget gate, and this is basically input gate. So what is the role of forget and input gate? The role of forget gate is to forget the previous information that you have from the previous cell state. So in this particular case, if you have this cell state here, which is denoted by OT minus 1, so if you want to forget something from this, you multiply it with the forget gate, and then this is passed further. And if you want to add something from the information that you have obtained from this particular gate, a particular cell, extra information that you have obtained from here, you can add it through input gate, and then that information will pass out to the next cell state, which is OT. So let us see, for example, if you have some information here OT minus 1, which I am representing, let us say by 2, 4 and 6, let us say. So if I want to forget this information 2, 4 and 6, then what we will do is we will actually multiply this with a vectors 0 comma 0 comma 0. So if I do by these, then what will happen is it will completely forget this state, because 246 will be multiplied by 0 0 0, and you will get 0 comma 0 comma 0 as the output. And if you want to add something which you have gained during this particular cell, which is because this is a part of a current cell, LSTM cell, which is at time t is equal to t. So if you want to add something, then what you can do is you can add, let us say 0.1, 0.2, 0.3. So finally at the output what you will get is 0.1, 0.2, 0.3. So what happened now is this information which was coming from the previous cell state is completely gone, and you have added extra information which you have passed to the next cell. And another operation that you can do is, let us say if you keep it as half, 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 and this particular vector if you keep it as 0, 0, 0. So if you do like this, that is if you keep half, half and half and 0 comma 0 comma 0, then what will happen? Can anyone tell what is this operation actually doing? Any one of you?
Sir, I think we will get the output as 0, 0, 0 only.
uh, no, actually what we will get is, we will partially forget the memory. you know we will partially forget the memory, like 50% of the memory will be gone, and we are not adding any extra information here. So if you observe here, you multiply this particular vector with half, half and half, so what you get at the answer is 1, 2 and 3. So 50% of the memory is lost from the previous cell state. But now once you and if you are adding 0, 0, 0, this means no information is added from the current cell state. So there is no information which is added. So the final answer is 1, 2 and 3 only, which is the which is so the basically for this particular cell of the LSTM, which we are focusing on, it has it has made the earlier memory, it has erased that by half, and then it has not added anything new. So it has just passed like this, which is 1, 2 and 3. Similarly, if the vectors are if the vectors are 1 comma 1 comma 1, and then if you have a vector which is of 0 0.2 0 0.2 0.2, so what it means is all the memory which is coming from the previous cell is added as such, and extra information is also added, which is due to the current cell. So now the important case which comes out to be is, which is very important, which will simplify our understanding. And that case is like if you have input vector which is 1 comma 1 comma 1, and another input vector which is 0 comma 0 comma 0 for the addition. So if this is the situation where you have 1 comma 1 comma 1 and 0 comma 0 comma 0 in the input gate, then what will happen is your C, this is OT I am representing here. So OT minus 1 will actually be multiplied by a vector of 1 comma 1 comma 1, and it's added with a value of 0 comma 0 comma 0. So what you get is answer is OT. So somewhere or the other, if you see it, it's nothing but there is a short circuit connection between the two. If you see, there is a short circuit connection between the two, because this 1 1 1 when multiplied with OT minus 1 is the same as OT minus 1, and you are not adding anything, so OT minus 1 is equal to OT. So it's a short circuit connection between the two, which is from the left to the right. So when there is a short circuit connection, then you can recall we have resnets. If you have gone through the deep learning architectures, then we have resnets. The resnet architectures, what they do is, in the resnet architecture, we have skip connections between the two blocks. So what they are doing is they are actually skipping the information in between. Somewhere or the other, it's helping in regularization, and problems of vanishing gradients are avoided. But this is somewhere related to that. You can see the skip connections that we use in ResNet is the same as the skip connections that we are using here in the LSTM cells. So here you can see a skip connection is formed if you multiply with the forget gate with the vector of 1 1 1 1, and with the additional information that you are trying to add, you are putting 0 0 0 0 there. Also, a skip connection is formed. So now let us recall how this will help us in our understanding of long-term dependencies in the statements. So if, let us say, if you have a block, language translator block. So in language translation, you have English translation going on here from English to German. So in English to German, when you are doing it, so what you are doing is you have another series of blocks, and these blocks can be different. So please note the number of blocks or the number of times instant that you have here will not be the same time instant here, because translation can be of varying length. So what you have is you have input here xi1, then you have xi2, then you have xi3, you have xi4, here you have yi1, yi2, yi3, yi4. So please recall, so the flow of this language translation is like this. So this is the typical language translation block diagram. So please recall last time when I was telling you that some of the words with which we start in English, not it's not necessary that with the same word you will start in French. So it can be different. So depending upon that, let us say if you have, this is the important word like, New Delhi or something like that, and maybe in the French the New Delhi is coming in the end. So you can see there is a long-term dependency between the two translations. So here you can see yi4 is dependent upon this xi1 through a very long route. And as I was telling you, as you progress down to this particular path, you can see there are number of non-linearities which are actually multiplying and cascading together. And there is a weak relationship between the output y hat with that of the input signal xi, as the weak relationship is because of the cascades of multiple non-linearities that you have if you try to formulate it using the equations. So now when you have LSTM, this is the particular case of RNN, and we had this drawback of long-term dependencies. But now in case of RNNs, what will happen? In case of LSTMs, the thing that is important is now you have short circuit connections in between the two. So you can short this, you can do a short circuit connections in between them. So if you have a short circuit connections between them like this, so what it means is there is a direct connection between xi1 and yi4. There is a direct connection between xi1 and yi4 through this short circuit connection. So now what will happen is this long-term dependency is gone in case of LSTM as it was in the case of RNN architectures. So the long-term dependency which was there earlier is gone because of this particular theme scene that we have discussed. So do you have any questions here related to what I was discussing? Any questions?
Sir, I had a query for the previous slide that you were talking about. So, what is the
Yes.
advantage of using a forget layer? Like, I think maybe even previous than
So what you are saying is, what is the advantage of using a forget gate?
yes, forget it, right?
See, sometimes what happens is, in natural language processing, sometimes when you have sequence of words, it's not necessary that you have to keep retaining that information further. Like for example, if I cook something like, uh, let us say if I say that I am walking, and then I suppose I say I am walking, and then I'll say, okay, I'm going to office. So there is no relevance of the previous statement with the second statement in the natural language processing. So sometimes it is important to forget the previous information and stay focused on the current information which you are actually working on. You understand? So depending upon the context of the statements, we have to see like whether the previous statement which we were talking about is actually relevant in deciding the importance of the coming statements or not. So if they are not relevant in deciding the content of the next series of statements, then we use the forget gate to completely forget it, and we are not using that past information in deciding the content of the coming statements. But in case if you want to retain it, like for example, if we say that New Delhi is some statements like related to New Delhi, and then we say that we are moving to Jama Masjid. Suppose, for example. So we all know that New Delhi and Jama Masjid are correlated, and it's in New Delhi. So somewhere or the other, that information we want to retain in the next statement. So that information retaining is important. So that's why you have forget gates and input gates, so that you can forget some portion of the earlier statements, and you can input the current context and try to add more information into that. So that type of thing is required. That's why we are using it. Okay.
Okay, so definitely this is highly case dependent.
Yes, it's a context dependent, like
Content.
how these statements are formulated, and how they are how they are that's why whenever you type something on your mobile, in case if you have, if your dictionary is on, then what will happen is, if you write something, you will get some options on the top.
Suggestions.
Yes,
Suggestions.
the suggestions are there on the top. So that comes because of the softmax layer that is applied at the outer at the output layer, and that softmax layer actually gives you probability on which one is higher, on the second one which is lower. So it will give you based on the probability that it is getting from your pattern of behavior, the way you are typing. So that prediction, or the softmax prediction, is because of
Okay. Thank you so much, sir.
any other questions from the audience. Okay, so if there are no questions, I guess I think from my side I'm done, because that was only the content that I had. I'm sorry I have finished much earlier than what was targeted of. But in case if you have any other discussion or related to this, I'll be happy to help you out.
Sir, I had a very basic query, if you allow. Uh,
Yeah.
in the recent papers that I have read these days, two keywords I've read a lot, but I'm not able to understand them. So,
Hmm.
the recent papers generally use these two keywords like freezing and unfreezing layers. So, what does
Hmm.
that mean?
Actually, freezing and unfreezing means, sometimes, what they want is, they don't want to touch the weights of a particular network while training, actually. So suppose, for example, every time when you do back propagation, your weights will keep on updating, right? So, like for example, in case of generative adversarial networks, we have, because we did this discussion last time. I hope you were there, I guess.
Yes.
So
Yes,
in
sir.
that case, we have two architectures. One is the generator, another one is the discriminator. Okay. So during the training process, what happens is, first of all, we during the training of the discriminator, what we do is we freeze the generator. By freezing the generator means we will not touch their weights and biases during the back propagation. We will keep them as such. Okay, whatever weights you have initialized that generator with, you will keep it as such. You will only train the weights and biases of the discriminator by doing back propagation. But when you want to do it for the other way around, you freeze the weights and bias of the discriminator, and then you train the generator. So by freezing means, you are not touching their weights, you are keeping them constant during the back propagation. Okay.
Okay. Okay. Thank you so much, sir. I request the audience, if they have any query, I can unmute them as well, or they can type in the chat box.
Okay, so
They can
let me
even raise their hands. Sir,
let, maybe I can share that my page, so that these students can, or maybe the faculties can get benefited from there. So here, here we have these, videos that I have created for my class here in DICT. So what I used to do is I pre-record them and then upload it during the class session. So here we have a lot of varieties of information. So whatever we missed out during our discussion. So for example, let me show you one such thing here. Like for example, in case of generative adversarial networks, I missed out some portions, like I didn't go into the details. You can watch it here. And for case of recurrent neural networks, which we were discussing today, if you see here, so we have multiple series of backpropagation derivations and vanishing gradient derivations. So it's actually going into the more details which I have not covered today in this particular part. So you can watch at your ease. They are all recorded. I hope these video sessions will also be recorded.
yes, sir, they are recorded, and we're going to upload them on YouTube as well.
Okay.
So
Okay,
we
okay,
have a
thanks.
question. The question
Okay.
is, Mamta ma'am, a general question: which type of neural network algorithm is good for to use to analyze satellite images?
Okay, so for satellite images, actually, it's better to use CNN architectures. And the important thing is, instead of neural networks will not be the wise way of doing it, because somewhere or the other, as I told you when we were discussing about these neural networks, what I was telling is, the images will be flattened out into one-dimensional vectors. So what happens is when you flatten the image into one-dimensional vector to be fed into neural network, the neighboring informations of these images, which is the pixel values, will get lost. So the best solution for that is to use convolutional neural networks instead of normal neural networks. But the important part there you have to keep in mind is that for the satellite images, what happens is you have lot of spatial relationship also along with the spatial relationship. You have spectral relationship also among the bands, so that has to be taken care of. So you have to use some other architecture also to add, to take care of that spectral relationship among the bands. So my suggestion will be to you use CNN and address both the bands, spatial bands as well as the spectral bands.
Okay, thank you so much, sir. Yeah. Any other query from the audience? Okay. So it was really an insightful session. It definitely cleared out so many basics of mine. I've been researching in this field only. Thank you so much.
Thank you so much.
And I hope that our audience has learned so much from these sessions. And thank you again for gracing this session.
Thank you so much for inviting me, and thank you for having such a good audience. And it's from wide areas, I guess. There are a lot of audiences from various parts of the country, and I'm hopeful that they will get benefited from these sessions, and maybe they can contact me anytime if in case they want some suggestions in terms of some sort of projects or something like that. That is always welcome, and we can work together and do some good piece of work.
Definitely, sir. Thank you so much.
Okay, thank you so much. Thank you.
Dear participants, the second session will start from 12:15 p.m. onwards. I request you to please join by that time. And I highly encourage all of you to please ask a lot of doubts. Thank you so much.